Hello, and welcome to the WebAssembly course. WebAssembly is currently a cutting-edge technology for the web. A few years ago, I remember when React entered the scene. It was a total game changer. For years, developers created apps with a library called jQuery. At the time, writing an app with React was utterly foreign to most web developers. If you were one of the lucky few to understand React, companies wanted to hire you. It was one of the most in-demand skills. Times have changed. Various frameworks have popped up over time. It's considered a standard skill for most web developers to know a front-end framework. History is repeating itself. A new technology has arose called WebAssembly. It's become very desirable to know WebAssembly in today's market. That leads us to the question, what is WebAssembly? WebAssembly is a language for the web. JavaScript has been the dominant language for decades. It's unlikely this fact will change. JavaScript is an awesome and powerful language. However, there are some shortcomings that can't be ignored. To better understand, let's talk about systems programming versus applications programming. When learning about programming, most students have various paths at their disposal. Generally speaking, we can categorize programming into two categories, which are systems programming and application programming. Application programming focuses on software with a UI. Users are meant to interact with this type of software, whereas system programming focuses on the hardware of a computer. Creating operating systems, game engines, industrial automation, and drivers can be considered the types of programs that can be done with systems programming. JavaScript is mostly utilized for application programming. These two worlds are not always separate. For example, a web server can be considered a systems program. We need web servers if we want to deliver JavaScript apps. You'll most likely work with a backend developer to work with servers. Technology is progressing very fast. We're starting to see a transition from desktop apps to web apps. However, not all desktop apps can be transitioned easily. For example, financial apps work fine on the web, but not video editing software. This is because video editing software requires access to a computer's hardware to process videos. Therefore, browsers need to expose access to a user's hardware. Do they use JavaScript or some other language? Like I said before, JavaScript is a beautiful language. I'm biased, but its popularity is undeniable. For user interfaces, JavaScript works great. For systems programming, that's another story. Designing a web or mobile app is mainly done through Photoshop. That's starting to change. Figma is a product for designing apps in the browser. You don't need to install a program to get started. Simply visit figma.com and you're good to go. In recent years, designers have fallen in love with Figma. They're using Figma to design apps over Photoshop. The most exciting thing about Figma is how it ports features from a desktop app to a web app. Unfortunately, processing and editing images require access to hardware. It's not easily done with JavaScript. It's possible but slow. In the resource section of this lecture, I provide a link to a blog post by the dev team. According to this article, developers struggled when launching Figma on time. For example, opening a file would take over 10 seconds. Thanks to WebAssembly, this time was reduced to about 3 seconds. Incredible, right? By using WebAssembly, developers can write apps for the web without compromising on performance. You may be thinking, doesn't this kill JavaScript? Not necessarily. The Figma team still uses JavaScript for UI elements like buttons, inputs, or events. For CPU-intensive tasks, they use WebAssembly. Unlike JavaScript, WebAssembly does not provide an API for selecting or modifying elements. It's not meant to write an application. Instead, it's intended to give developers a way to access the system's hardware. If we need to handle user interactions, JavaScript will work. WebAssembly is for computational tasks. Hopefully, this clears up the goals of WebAssembly. You may be itching to get started, but there's one more thing I want to mention. Typically, developers will not refer to WebAssembly as a language. Technically, it is, but there's a better word to describe it. WebAssembly is seen as a compilation target. A compilation target refers to the language targeted by a compiler. If you're familiar with TypeScript, you may be familiar with this concept. To the dismay of many developers, TypeScript does not run in the browser. It has to be compiled from TypeScript to JavaScript. JavaScript can be considered a compilation target. It's the language targeted by the compiler. Similarly, WebAssembly is not meant to be written and read by humans. Instead, we can use our favorite programming language. After we're finished writing our app, we can compile it to WebAssembly. You may be thinking, why should we use another language? There are two main reasons for writing WebAssembly with a different language. Firstly, it allows developers to continue writing code in their preferred language. A C++ developer can write WebAssembly without dedicating their weekend to learning a new language. They can get started right away. Secondly, WebAssembly is not an easy language to learn. Let me show you an example of WebAssembly code. In my editor, I've opened a WebAssembly text file. This file is huge. There are about 400,000 lines of code. Even if I wanted to, I don't think it's possible to go over every line of code in a single course. In another tab, I have a Rust file with the original code. Instead of thousands of lines of code, the original source code is less than 40 lines. You tell me, do you want to write 400,000 lines of code or 40? I'm gonna guess 40. The creators of WebAssembly didn't intend for developers to write WebAssembly code. Rather, they recommend choosing another language. Thus, you should treat WebAssembly as a compilation target. The question is, which language should we use? WebAssembly supports dozens of languages. We can use C++, C#, Java, Go, Python, Rust, etc. The list goes on and on. It can be challenging to choose a language. For this course, we're going to be using a language called Rust. Rust is considered the most beloved language by developers. But don't take my word for it. Stack Overflow conducts the largest programming survey in the world. Thousands of developers submit responses to their survey. For the past few years, Rust has been rated as the most loved language. Scott Logic, the largest newsletter for WebAssembly, conducts its own survey for WebAssembly developers. From their survey, Rust is considered the most popular and desirable language for WebAssembly. You're very likely to encounter a WebAssembly project written with Rust out of all the languages available. In this lecture, we are going to install Rust on our machines. Before we do, let's talk about Rust. As I mentioned before, it's one of the most loved languages by developers. Why is that? What makes it so unique? Designing a programming language is a tough job. Communities will not hesitate to point out the pain points of a language. Rust was designed to solve the problems present in other languages. While not unique, Rust is a statically typed language. These types of languages allow the compiler to run checks on our data and functions. Thus, we can catch errors during compilation. This feature does force developers to write more code. One of the most significant drawbacks of a statically typed language is readability. Rust introduces type inference to help with readability, which we'll talk about in a future lecture. Out of all the languages available, Rust is highly memory efficient. If you're a JavaScript developer, memory may not be something you think about frequently. Whenever you define a variable, you're taking up memory on a user's machine. One variable is not going to kill a user's browser, but hundreds of them can. Rust emphasizes memory safety. A majority of popular languages employ a garbage collector. It's a program that continuously checks your application for unused memory. Garbage collectors can automate the action of freeing memory. The problem with garbage collectors is that they're slow and unpredictable. We don't have control when they run. When they do run, they require additional resources to handle freeing memory. Unlike other languages, Rust guarantees memory safety. It's completely aware of when memory should be free. Periodic checks are not performed. Instead, it knows exactly when memory can be released. Lastly, Rust is highly performant. It's just as fast as C or Java. Since it's a memory-efficient language, you never have to pay for things you aren't using. If this sounds foreign to you, that's completely fine. Throughout this course, we'll get first-hand experience with these features. Let's move on to installing Rust. If you're on a Mac or Linux, Rust can be installed through the terminal. You should run these commands to begin the installation. After installation, a success message should appear. Rust is a relatively easy language to install. If you're on a Windows machine, the installation is slightly different. In the resource section of this lecture, I provide a link to the installation page of Rust. Windows users can run a downloadable installer. There's a 32 and 64-bit version. In most cases, the 64-bit version should work for most users. Download the installer and run the installation. It's a standard installation process. Just click Next until the program is installed. I'm going to quickly install Rust on my machine. After installation, 3 tools are going to be installed on your system. They are accessible via the command line. The first tool is called Rust Up. It's a tool for managing different versions of Rust. Other projects may require different versions of Rust. Ideally, you will want projects to run on the latest version. In some cases, you may need experimental or beta features. Through the Rust Up command, you can install a nightly version of Rust. The second tool is called Rust C. Rust needs to be compiled from human-readable code to binary code. The Rust C command will perform this process for you. Normally, you won't need to run this command because of the cargo tool. This command is responsible for managing dependencies for your project. It can also compile your project. Behind the scenes, it runs the Rust C command. Therefore, you can skip running the Rust C command. Let's explore these tools. We're going to skip the Rust C tool since the cargo command runs this tool for us. First, let's explore the Rust Up tool. Currently, I'm in an empty directory with the command line opened. If you're using Visual Studio Code, you can open a new terminal by navigating to Terminal, New Terminal. The Rust Up tool is not hard to use. It's very likely you'll be using it to upgrade Rust. We can upgrade Rust by typing the Rust Up update command. We've installed the latest version of Rust. It shouldn't take long for Rust to realize it doesn't have to update our project. In most cases, you will use the Rust Up command to upgrade your Rust version, which I always recommend doing. New releases are frequent from the Rust team. In the resource section of this lecture, I provide a link to a book called Rust Up. One of the things I love about the Rust community is their effort to share basic knowledge with beginners. This book provides a basic overview of the Rust Up tool. It's completely free and aimed at newcomers. If you would like more information about this tool, I highly recommend reading this book. Let's move on to the cargo tool. Cargo is analogous to NPM. Cargo is to Rust as NPM is to JavaScript. Simple, right? In the resource section of this lecture, I provide a link to a registry called Crates. You can find community-contributed packages on this site. It's very popular with the Rust community. Almost 9 billion downloads have been made. The Crates tool has various commands for creating a project. Let's give it a try. Switch back to the command line. We can create a new project by typing the cargo init command. After a few seconds, the command should have generated a new project. In the following lecture, we're going to begin exploring the project generated by cargo. In this lecture, we are going to explore the starter project generated by cargo. Let's begin with the root files. The first file is a git ignore file. Git is a popular tool for managing projects. You're very likely familiar with it. It's a standard tool among developers. You can write a list of files to prevent them from being committed. By default, cargo recommends not committing a directory called targets. Our project doesn't have this directory, but it will in the future. The target directory contains the executable generated by Rust. In a moment, we will look at building the project. Moving on, the next file is called cargo.toml. It's a configuration file for Cargo. We can compare it to the package.json file for Node.js projects. It's possible you may not have syntax highlighting for this type of file. Out of the box, Visual Studio Code does not support TOML files. We can install an extension to enable syntax highlighting. Switch over to the Extensions tab. We're going to search for an extension called Even Better TOML. Install this extension for VSC. It's going to provide support for TOML files. In addition, this extension can validate and format our code. After installing this extension, let's switch back to our configuration file. The code should be highlighted in your editor. Perfect. Let's review the file together. TOML files are very simple. At the top of the file, we have something called a table. A table is a fancy word for describing different sections of the TOML file. It keeps our configuration organized into groups. Tables are written with square brackets surrounding the name of the table. Cargo will define two tables called package and dependencies. The package table contains settings for describing the project. Settings are written as key value pairs. So, for example, we have the name and version of our project. You're more than free to modify these values. However, there are rules you should be aware of when changing these values. Keep in mind, they'll be read by Cargo when it's managing or compiling your project. Luckily, there are descriptions for these settings. If you hover your mouse over the name key, a description will appear with detailed information. According to the description, the name key may only contain alphanumeric characters. You should always consult with the documentation before modifying these values. Speaking of documentation, I provide a link to the official documentation page for this file. This page goes into detail on every setting available. Feel free to check it out after you've finished this course. First, let's go back to the configuration file. Out of these settings, the most critical setting is the addition. Rust is continuously evolving. As changes are made to the language, there are possible breaking changes. For the best backward compatibility, Rust is broken into editions. As of this course, the latest edition is 2018. However, it's 2021. Rust is due for a new edition within the next 2 months. If your project contains the 2021 edition, that's perfectly fine. Our code will be compatible with future editions, so you don't have to revert this option to 2018. There's another table called dependencies. If you would like to install a community package, you can list it under this table. By default, this table will be empty. Dependencies are a topic we will explore in a future lecture. That wraps up the cargo.toml file. The last thing generated for our project is a directory called source. We can write our project code inside this folder. Cargo creates a file called main.rs. It's the main entry point of our project. If we open this file, we'll be given a basic example of a Rust file. Rust files are identified by their extensions, which is rs. It's possible you may not have syntax highlighting for Rust files. There's a community extension for Rust files. The name of this extension is called Rust. Install it for VSC. After installing it, we can switch back to our file. The code generated by Cargo will output a Hello World message. We'll talk about the details in a future lecture. For now, let's try testing the compiler. In the terminal, we can compile Rust by running the cargo run command. Behind the scenes, Cargo will use the Rust C tool to compile projects. Most developers prefer to compile Rust through Cargo. The compiler will tell us how long our project took to compile. It'll even run the project after compilation. Projects will not run unless our program is error-free. If we had an error, the console would output information related to the error. This default behavior allows us to catch errors before production. In some cases, You may not care about the status of the builds. You can ignore the statuses by adding the -Q option to the cargo run command. By adding this option, the statuses are ignored from the output. We only get the output from our program. Moving along, you can find the build of your project in a folder called Targets. If this folder doesn't exist, Cargo will create it beforehand. The files in this folder can be deployed to production. In addition to the target folder, a file called cargo.lock is created. If we open this file, a comment will be written at the top. It says the following: "This file is automatically generated by Cargo. It is not intended for manual editing." As the comment says, we can safely ignore this file. Cargo completely manages it. Congrats! We've successfully created and built our first Rust project. In the next couple of lectures, we're going to begin learning the fundamentals of Rust. We'll continue working on our new project. In this lecture, we are going to start our journey by learning about variables. This course assumes you have some experience with programming. Learning a new language is much easier the second time around. While the syntax may be different, the concepts are very similar from language to language. Variables are still variables. Functions are still functions. Conditional statements are still conditional statements. So on and so forth. You get the picture. Variables in Rust serve the same purpose as variables in other languages. They're containers for data. Throughout this course, we will be working inside the source/main.rs file. I recommend opening this file before starting a lecture. Inside this file, Cargo has defined a function called main. I know we said we would start with variables, but let me quickly introduce functions. Functions are blocks of code for performing a particular task. If you have a background in JavaScript, you would use the function keyword to define a function. For Python developers, you would use the define keyword. For Rust developers, function definitions start with the fn keyword. It's all the same. The fn keyword is followed by the name of the function, a list of arguments, and then the block of code. Our apps must define a function called main. By default, Cargo will search for a function called main during compilation. If we were to rename this function, the compiler would complain. It's always guaranteed this function will run once. We're going to empty the contents of the function. We'll be starting fresh. The main focus of this lecture is variables. We can declare a variable by typing the let keyword. Next, we can give our variable a name. For this example, let's set the name to myname. For the value, we're going to store our real name or whatever name you prefer. After declaring this variable, Rust is going to throw a warning. Assuming you have the Rust extension enabled, there should be a yellow squiggly line below the variable name. We can hover our mouse over the variable to learn about the error. Just in case if you don't see an error, you can produce the error by running the cargo run command in the terminal. The compiler won't hesitate to output the same error. Regardless, the error message should be the name. According to the compiler, there's a problem with the variable name. At times, Rust can be an opinionated language. Variables must be snake-cased. They can't be camel-cased. It's a standard practice in Rust projects. Let's convert the variable name to snake casing. Learning to adopt a specific formatting practice can be tedious, especially if you're used to writing code differently. However, it's worth it to be consistent with the community. There are a couple more features I want to point out. Firstly, statements must end with a semicolon. If you have a background in JavaScript or Python, semicolons are optional. Statements in Rust must end with a semicolon to indicate the end of the line. If we were to remove this character, the compiler would throw an error. Errors are indicated in the editor with a red squiggly line. According to the compiler, it expected a semicolon. Let's add it back in. Moving along, Another warning gets thrown by the compiler surrounding the variable. The error will tell us the variable is unused. For this example, we are going to ignore this warning. It's not the end of the world. Alright, one more thing before we move on to the next topic. Variables are immutable. Mutability is another way of saying a variable can't be changed. Once a variable is initialized, we can't change it to another value. Therefore, they're immutable. This design forces developers to be aware of how their variables will be used. That doesn't mean mutability is bad. It is possible to make a variable mutable. Let's try mutating the myName variable to a different value. An error gets thrown by the compiler. It's telling us we can't modify an immutable variable. Variables can become mutable by adding the mut keyword before the variable name. Let's add this keyword to the myName variable. With a single keyword, the error has gone away. Mutable variables must be explicitly declared with the mut keyword. You should keep this in mind when working with variables. Let's continue talking about Rust in the next lecture. In this lecture, we are going to discover data types by diving into functions. As we've learned, functions are declared with the fn keyword. Rust automatically calls the main function. Writing our entire logic into one function may not be the most efficient way to write code. Let's try defining additional functions. Before we do, let's empty out the main function to start with a fresh slate. Above the main function, define a new function called add. As the name implies, we're going to define a function for adding two numbers. Our function should return the results. We can start by adding arguments to the function. We're going to limit our function to two arguments. They'll be called num1 and num2, respectively. After adding these arguments, the compiler will throw an error. Arguments must be explicitly typed. If you can recall, we never had to add types to our variables. Variables can be inferred. Let's look at an example. Inside the main function, let's define a variable called foo with an initial value of false. The data type of the foo variable is a Boolean type. We can hover our mouse over this variable to double check the data type. Rust can guess the data type of our variable based on the value we initialized it with. This feature is called type inference. All variables must have a data type. Whenever possible, Rust will help us with annotating a variable with a data type. In some cases, variables may need to be given a type explicitly. For example, let's say we don't initialize the variable with a false value. By removing this value, Rust can't guess the data type of our variable. It'll throw an error. Therefore, we should help the compiler by annotating the variable. Adding a type to a variable is called a type annotation. A type annotation can be added by adding a colon character after the variable name. This character is followed by the name of the type. In the resource section of this lecture, I provide a link to a list of types in Rust. The type we're looking for is called Boolean, or bool for short. Back in our editor, let's apply this type to our variable. After adding the type, the compiler has been satisfied. Hopefully, you can probably guess why the add function is not working. If we hover our mouse over the function's arguments, the compiler is informing us of its inability to infer the types. This doesn't just apply to our function, but all functions. Function arguments must be annotated with a type. The goal of our function is to get the sum of two numbers. Therefore, our function's argument should be annotated with a data type suitable for numbers. Believe it or not, Rust has about a dozen data types for numbers, which may appear abnormal. With so many choices, which data type do we use? The most common data type is I32. For example, Let's update our foo variable to a random number. We can hover our mouse over the variable to inspect the data type. By default, Rust infers a data type of i32. It's a standard type for numbers. You can refer to the page I provided earlier for a complete list of data types for numbers. But you may be asking, why are there so many data types for numbers? Keep in mind, Rust is a memory-efficient language. Not all numbers are equal. Some numbers can range from 1 to 100. Other numbers can range from 1 to 1 billion. As you can imagine, the larger a number, the more memory it occupies. We can save memory by being precise with our data types. If your variables will store small numbers, you may benefit from using a data type suitable for small numbers. For example, the i16 data type can store small numbers. If you need to store large numbers, you can use the i64 data type. By default, Rust likes to use the i32 data type to cover most cases. I think it'll be suitable for our add function. Let's annotate both arguments with the i32 data type. We're not finished yet. The return value should be annotated too. This step is optional if we're not going to be returning a value. However, our function will return the sum. Thus, we should annotate the return type. Return values can be annotated by adding an arrow after a function's argument list. This arrow is followed by the data type. We'll set the data type to i32. The last step is to add the arguments together. Inside the function, add the following: return num1 plus num2. The return keyword can be used to return a value. Interestingly, the return keyword is optional. Rust will automatically return the value if the last line in the function is an expression. We can altogether remove the return keyword to get the same behavior. The return key is required if you want to return the function earlier than planned. Let's use our function. Instead of assigning the foo variable to a number, let's set it to the value returned by the sum function. We will pass in two numbers. Behind the scenes, Rust can infer a variable's type from a function's return value. We can hover our mouse over the foo variable for further proof. We don't need to annotate the foo variable. Rust is capable of annotating the type with the function's return type. Isn't type inference awesome? It keeps our code readable. It's time to output the number. So far, we haven't compiled our project. Nothing would happen if we were to compile it because we haven't told our program to output information. Let's learn how to output information in the next lecture. In this lecture, we are going to learn how to debug an application with macros. Macros are an advanced subject. Unfortunately, we won't be able to dive into how macros are created. There isn't enough time to review the code of a macro. So instead, this lecture will be a light introduction to them. Don't worry, it'll be enough to work with WebAssembly. So, what are macros? First, we need to understand something called metaprogramming, which can be a trippy concept. It's when a program can write a program, literally. Copying and pasting code is a classic developer move. We all do it. What if we could write a program that copies and pastes code? I'm oversimplifying it, but that's metaprogramming in a nutshell. Bringing it back to Rust, a macro is a feature for writing code in our program. Rust will copy and paste code defined in the macro, which is a form of metaprogramming. It can be a difficult concept to wrap your head around. Writing a macro is very difficult. Luckily, it's not something we'll need to do. As long as we know how to use them, we'll be good to go. Using a macro is very easy. The syntax is similar to a function. In our main function, we are storing the sum of two numbers in a variable called foo. Let's output the result onto the console. Rust defines a macro for this specific action. Below the foo variable, let's add a macro called println. The letters ln are short for line. Almost immediately, you'll notice a strong similarity between calling a macro and calling a function. We write the name of the macro followed by a pair of parentheses. The biggest difference between a macro and function is the exclamation mark character. It'll always appear after the name. This is how you can identify macros. Another similar feature macros share with functions is arguments. In between the parentheses, we can pass on a value to print the terminal. Let's try passing in a hello world message. Next, let's run our program with the cargo run command. The message gets outputted as desired. However, we get a warning from the compiler. It's telling us the foo variable is unused. Let's replace the string with the foo variable in the print macro. The compiler will throw an error. It's very strict with the types of values we can pass onto macros and functions. On the one hand, it's very convenient, but not in this case. There are scenarios where we are going to need to debug values other than strings. We might want to debug arrays, numbers, or booleans. Luckily, the print line macro supports formatting. We can inject values into a string. Let's replace the foo variable with a string. Inside the string, we're going to add a pair of curly braces. The curly braces act as a placeholder. Before Rust outputs the string, it'll replace the placeholder with a value of our choosing. We can add a value as a second argument to the print line macro. Let's try running the cargo run command. In the terminal, the variable's value gets displayed. Perfect. We're able to debug our values by inspecting them in the terminal. The print line macro is more flexible than you can imagine. For example, what if we want to output multiple values? The argument list is limitless. Inside the string, let's add another placeholder. An error will be thrown by the compiler. It's unable to find a value for the second placeholder. Let's add a Boolean value as an argument to the macro. Lastly, let's compile our code. Rust was able to replace our values. The order of placeholders will correlate to the order of arguments. The first placeholder will be replaced with the second argument. The second placeholder will be replaced with the third argument. So on and so forth. In some cases, we may want to reuse a value. The print macro supports positional arguments. I'm going to remove the Boolean value. After removing it, the compiler will throw the same error as before. Instead of adding a new value, we can point to a specific argument by adding a number inside the placeholder. The number is a position to a value in our argument list. Positions are zero-based. Therefore, 0 will point to our foo variable. Let's add zeros to both placeholders. Next, let's compile our project. Both placeholders are replaced with the number. There's one last trick I want to show you. In some examples, you may see developers use a different placeholder. The syntax is slightly different than a regular placeholder. Let's reset the string to a regular placeholder. Inside the curly braces, let's add a colon and question mark character. This type of placeholder works for complex values. Rust gives developers the flexibility of manipulating a value before it gets outputted onto the terminal for debugging purposes. If a developer decides to do that, we will need to use this placeholder. Let's try compiling the project. We get the same output as before. It's not apparent as to why we would use this placeholder. I promise you, when we start working with complex values, this placeholder will come in handy. We've talked a lot about macros. They're similar to functions. Functions and macros are written the same, with the exception of the exclamation mark symbol for macros. They both have a list of arguments. Conceptually, they can achieve similar goals. We can outsource logic into both features. So, what are the differences? Macros support the following features: variadic arguments, pretty syntax, and metaprogramming. These topics are beyond the scope of this course. I want to emphasize you don't need to know how to write macros for this course. The macros shipped with Rust will suffice for most cases. As long as you know how to use them, everything will be smooth sailing. Let's continue our journey in the next lecture. In this lecture, we are going to discuss control flow in Rust applications. There are two options for controlling the flow of an application's logic. We have if-else statements and match expressions. Both options will be explored in this course. We'll start with if-else statements. They're easier to understand. Previously, we left off with macros to print a message to the terminal. What if we want to display different messages based on a condition? Let's say we're creating a program for an online shop. Businesses love offering free shipping if a purchase exceeds a minimum threshold. For example, let's say we want to offer free shipping on purchases over $50. Before applying free shipping to a user's purchase, we should check the total. We can use if-else statements. They function similarly to if-else statements in other languages. First, let's rename the foo variable to total. Above the print line macro, let's add the if keyword. An if statement is written with the if keyword followed by the condition. In some languages, conditions are wrapped with parentheses. Parentheses are not required with Rust. We can immediately write the condition. The condition must be an expression that evaluates to a Boolean value. For example, we can't set the condition to the total variable. The compiler will complain about the value. Taking a closer look at the error, the compiler is expecting the Boolean type, but received an integer type. We should update the condition to return a Boolean value by using a comparison operator. In the resource section of this lecture, I provide a link to a list of operators. This table will present an overview of available operators in Rust. Unfortunately, these operators are not grouped by category. You will need to do some digging to find what you're looking for. From this list, we are going to use an operator for comparing two values. Let's go back to the editor. In the condition, we will compare the foo variable to 50 with a greater than operator. If the foo variable is greater than 50, we will run a block of code. We can add the block of code with curly brackets. For this scenario, we are going to tell the user they are qualified for free shipping. Rust supports else and else-if statements. If a user's total is greater than 20, we should nudge them to add more items to their cart for free shipping. At the moment, this message will never get printed because the total variable will never store a number above 50. Therefore, the terminal will not output a message. Typically, we should provide feedback to the user. Let's add an else-if statement. The condition for this statement will check if the foo variable is greater than 20. In the else-if block, we will print the following message. If you add more items, you can qualify for free shipping. An else-if block will run if the condition fails for the if block. It must be chained after an if statement or another else-if statement. Otherwise, the compiler will throw an error. We can expect this condition to evaluate to true. Lastly, we will add an else statement. The else block runs when the other conditions fail. It's seen as a last resort. If a user's purchase falls below $20, it's unlikely they will want to add more items. We should output a message that says no free shipping. By chaining conditional statements, we can control the flow of logic. Let's give our application a test by running the cargo run command. The program outputs the message from the else-if block. Feel free to modify the numbers we passed into the add function. The message should change based on the sum. In the next lecture, let's look at an alternative solution. In this lecture, we are going to explore an alternative feature to conditional statements. Rust has a syntax feature called match expressions. They allow us to perform a comparison against a series of patterns. If there's a match, we can run some code. Theoretically, we can control the flow of an application with match expressions. After reviewing the syntax for match expressions, we'll discuss the differences between match expressions and conditional statements. Let's get started. At the moment, we're informing the user of their qualification for free shipping. However, we haven't updated the total. If the user has free shipping, their total will remain the same. On the other hand, if they don't qualify, the shipping price will need to be added on top of the total. Theoretically, we could update the total inside the if block. For demonstration purposes, let's learn how to perform this action with match expressions. First things first, the total variable will need to be mutable. As we learned previously, variables are immutable. Updating the total will require the mute keyword on the total variable. Next, let's create a variable to store a Boolean value. Below the total value, define a mutable variable called free shipping with an initial value of false. We're going to assume the user does not qualify for free shipping. This variable should be updated inside the if block. We'll toggle the value to true. The next step is to check this variable to calculate the final cost. After the series of conditional statements, let's add the match keyword. The match keyword performs a similar operation to a conditional statement. We can use match expressions to compare values. After typing the match keyword, we need to provide a value to perform comparisons on. We'll add the free shipping variable. Next, we need to add curly braces. Inside the curly braces, we need to provide a list of values to compare against the variable. Unlike conditional statements, match expressions are exhaustive. This means we need to account for every possibility. In our example, our variable is a Boolean. Booleans can have one of two values. They can be true or false. We are required to account for both scenarios. For example, inside the block, let's handle the scenario where the free shipping variable is true. Then, after the value, we can add a fat arrow. The code after this arrow is the code to execute if there's a match. We'll update the total property by adding 0, which essentially means they won't have to pay for free shipping. After adding this value, we're thrown an error. The error states we haven't covered a false value. Rust is very strict and demanding with match expressions. We can't omit a possibility. All possibilities must be handled. Despite the strictness of this feature, it's prevalent among Rust developers. This behavior can be good for developers. It forces us to handle all scenarios. If we forget a possible value, the compiler will warn us ahead of time. You may want this behavior when working on large applications. As your application grows, it's possible to overlook a pattern in your control flow. Rust can warn us when this problem happens. Let's handle a false pattern. If the free shipping variable is false, we're going to update the total variable by 5. The free shipping variable is false. Thus, we should charge the buyer for shipping. They haven't met our threshold. At the end of the function, let's print the total variable. Keep in mind, the print line macro will not output numbers unless we format the string. Let's compile our project. It looks like I'm out of luck. My total is below the threshold for free shipping. I'll have to pay for shipping on my purchase. As you can see, our app works. We were able to update the total variable with a match expression. As I stated before, it's possible to exclusively stick with conditional statements. However, matches are more useful for their strictness. We can take our expression a step further. The match keyword creates an expression. As a reminder, expressions are pieces of code that evaluate a value. For example, arithmetic operations are expressions. such as the return value in the add function. The match keyword can return a value. Theoretically, we can refactor our current solution to update the total variable. Let me show you what I mean. Instead of updating the total variable in the patterns, we can move the assignment outside the match expression. This code will result in the same behavior. The values returned by our patterns will be returned by the expression. Thus, the total variable will be updated. We can run our compiler to view the results. As you can see, everything works like before. You're more than free to use the previous solution. In my opinion, I think this solution is more readable. It's clear that we're trying to update the total variable based on a condition. Match expressions seem great, so what's the catch? If we have unlimited patterns, we need to handle them all. The current expression will have two possible values. Either the free shipping variable is true or false. It can't be any other value. What if we run a match against a number? Let's find out. Below the first match expression, let's perform a match against the total variable. Inside the expression, we'll check if the variables match the numbers 1 or 2. In both patterns, we'll output a message. There's an infinite amount of numbers. The compiler is complaining we haven't accounted for all patterns. But how can we? We don't have time to enter every number imaginable. Luckily, the match operator has us covered. We can insert a wildcard character to catch patterns we haven't added. Inside the block, add an underscore character. The underscore character is a fallback pattern. If the match operator cannot find a match, the code from this pattern will run. In this example, we will print a message that says the following: no match found. Let's compile our project. As you can see, the match operator was not able to find a match. It defaulted to the underscore pattern. There's a lot more we can do with matches, but this information will suffice. There are a couple more topics I want to cover before moving on to WebAssembly. I'll see you in the next lecture. In this lecture, we are going to take a look at arrays. Storing a list of data is a common type of action you may want to perform. For example, we can store lists of posts, users, purchases, etc. Arrays are commonly used in languages to store a list of data. Rust supports arrays, but there's one caveat: the size of an array is fixed. For example, if the size of an array is 5, the array may never contain more than 5 values. We can't add new items to the array. Rust constrains the size of an array after initialization. Let's give arrays a try. At the bottom of our function, let's create a variable called items. An array can be created by adding a pair of square brackets. The square brackets may contain our collection of values. Each value is separated by a comma. For this demonstration, let's add 5 numbers. The size of the array is 5. We can hover our mouse to verify the size. Our editor has annotated the array. This feature is another thing to be aware of. The values in the array must be of the same type. In our example, the types are integers. After the type, the size of the array is written. We have the option of annotating the array. After the variable name, let's add an annotation. Arrays can be annotated by adding a pair of square brackets. The annotation is going to need 2 pieces of information. The first piece of information is the data type of the array. For this example, we are creating an array of integers. Next, we need to add a semicolon followed by the size of the array. This step is optional, but you may need to know how to annotate an array if the compiler can't infer the array. Let's try logging the array by using the print line macro. Arrays can't be printed. We need to use a placeholder. Inside the string, add a debug placeholder. For the second argument, we'll pass in the array. Lastly, let's try running the cargo run command. The array gets neatly formatted in the console. There's not much else to say about arrays. An array must have a fixed size, and the values in an array must have the same type. In the next lecture, we will begin looking at another data type for storing a collection of data. In this lecture, we are going to explore another type for storing a collection of data called vectors. Typically, vectors are more popular than arrays. They both serve the same purpose. A vector can store a list of data. The data type in a vector must be of the same type. So, what's the deal? Why is there an alternative type? Arrays have a fixed size. If the size of an array is 5, we can't store 4 or 6 values. The size must exactly be 5, whereas vectors are dynamically sized. They're much more flexible than arrays. Pushing or removing data from a vector is allowed. Vectors can be as large as we need them to be. There are other differences, but this is the most important difference. It seems like vectors are superior in every way. However, vectors take up more storage. Rust needs to allocate memory for a vector, which is not as efficient as arrays. While vectors are more popular with Rust developers, there are use cases for arrays. For example, let's say you're creating a financial application. Users may want to view the price of a stock over the course of a week. The stock market is open 5 days a week. This type of data can be stored in a vector or array. However, arrays may be better suited for this task. We only need to store 5 values. Therefore, an array will suffice. Arrays are great for smaller collections with a fixed size. Vectors can be used for everything else. Enough theory. Let's create some vectors. Rust gives us 2 options for creating a vector. I don't consider either option superior over the other. Feel free to use whichever syntax you prefer. Below the items array, let's recreate the same array. The name of the variable will be called vector items. The first option for creating a vector is with a macro. We can set the variable to the vector macro. This macro doesn't need to be called like a function. We can immediately start creating the collection with a pair of square brackets. Like before, vectors are a list of comma-separated values. Let's input the same values of our array. Feel free to copy them over. Next, let's explore the second option for creating a vector. We're going to recreate the same vector. Below the variable, define a variable called vector items2. The value for this variable will be a function called vec::new. We're utilizing a feature called structs, which is short for structures. A structure is similar to the idea of an object or class. They are containers for multiple pieces of data. We aren't going to dive into structures for this course. It's enough to know how to access a function from a structure. We can access a function by typing 2 colons. In this example, we are calling the new function to create a new vector. By default, the vector will be empty. We should start pushing values. Before we do, let's add the mutable keyword to the variable. Otherwise, we won't be able to push values into the vector. New values can be inserted into the vector by calling the push function on the vector. We can pass in a value to push into the vector. Let's push the same 5 numbers we had in the previous vector. Creating vectors is a relatively simple process. There isn't a difference between these 2 syntaxes. Behind the scenes, the vector macro is calling the new function to create a vector. Afterward, it's calling the push function to add new values. You can think of it as sugar syntax for creating a vector. At the end of the day, there isn't a difference in performance. Choose whichever option feels right to you. To test our code, we should print these vectors. At the bottom of the function, I'm going to quickly print both vectors. Since we're dealing with vectors, we will need to format the string using the debug placeholder. Make sure you're typing the colon and question mark characters inside the curly brackets. Inside the command line, let's compile the project. 3 collections are printed to the console. The first collection is an array, while the other 2 collections are vectors. They look very similar. Internally, they are very different. As we discussed before, they have their use cases. If you need a fixed-sized collection, use an array. Otherwise, stick with a vector. Let's continue our discussion of Rust in the next lecture. In this lecture, we are going to learn how to create custom types with structures. We are going to be starting on a fresh project. I think the previous project was starting to get cluttered. I recommend moving into an empty directory. Once you're in an empty directory, initialize a new project by running the cargo init command. Next, let's open the main.rs file. A structure can be thought of as a user-defined type for grouping data. It's common for data to be grouped. For example, let's say we were creating a banking app. An account will hold various types of data such as the owner's name, balance, interest rate, etc. It's completely possible to avoid structures altogether. Theoretically, we can define variables for each of these values. However, if we need to create a new account, we will need to remember the values in an account. By creating a structure, we can easily make sure every account has the same set of values. Rust enforces a strict model on structures. Let's take a closer look at structures by creating one. At the top of the file, a structure can be defined by adding the struct keyword. Next, we need to give our structure a name. Let's give our structure the name of bank account. It's time to add fields into the mix. A field represents a single value in a structure. We can describe the makeup of structures with fields. The fields are enclosed with curly braces. The names for fields follow the same rules and conventions as variables. In addition, we must explicitly set the types of our fields. For this example, we will add 2 fields called balance and verified. The balance field will have an integer type. As for the verified field, it'll have a Boolean type. Our structure is ready. We've defined the data type, but we're not using it. If we want to create values with this structure, we can do so in a function. Inside the main function, we'll replace the existing code with a variable called myAccount. The value for this variable will be the bank account structure. Inside the curly braces, we must add the same fields defined in the bank account structure. This feature is one of the benefits of using a structure. We can hover our mouse over the structure to view the errors by the compiler. Our compiler is telling us we are missing 2 fields from the structure. It acts as a reminder whenever we're creating a new value with a structure. Let's add the balance and verified fields with random values. After adding these fields, the error should go away. Let's print the fields with the print line macro. We can access a specific field with dot notation. For example, let's try printing the balance field. Inside the print line macro, the string will contain a debug placeholder. For the second argument, we will pass in the myAccount.balance field. Let's do the same for the verified field. Lastly, let's compile our project with the cargo run command. As you can see, we're able to access a field's value with dot notation. Structures are very powerful because they allow us to group data. In addition, we benefit from its strictness. If we ever update a structure, our compiler will inform us of variables that aren't compliant with the structure. In this lecture, we are going to discuss a core concept called ownership. I consider Rust to be a reliable language for its memory safety. We've talked about memory before, but how does Rust achieve memory safety? That's what I want to talk about in this lecture. We should take the time to understand the underlying features that make Rust a memory-safe language. One of the biggest problems in the programming world is memory leaks. They are a plague to most programmers. A memory leak is when a program fails to keep track of its data properly. Let's say we had a variable for storing a number. Variables take up memory on the user's machine. At some point, we're not going to need the variable anymore. If we forget to release memory, we've created a memory leak. Instead of reusing memory, programs will need to reserve additional memory for additional resources. In some languages, we need to perform the operation of deallocating the memory. However, Rust can clean memory for us. We don't need to write additional code to benefit from this feature. This behavior makes Rust highly popular among system programmers. It emphasizes cleaning memory. Under the hood, Rust utilizes an ownership model. Values assigned to a variable are owned by that variable. It is as simple as that. Whenever we create a variable, we're creating a new owner. Rust will automatically deallocate memory when a variable is not needed anymore. In Rust lingo, you may hear this process referred to as dropping a value. This behavior does carry some consequences we should be aware of. Let's take a look at an example of ownership gone wrong. We are going to continue working on the same project from the previous lecture. We have a variable called myAccount. This variable has ownership of the value. The question is, when does the value get dropped? Values are dropped when the function is finished running. In this example, the main function is automatically called whenever we run the program. Once the main function is finished running, Rust will release the memory from the variables defined inside of it. We don't need to make further changes to benefit from this behavior. Let's say we want to outsource the print line macros into different functions. We will define two functions for printing the balance and verified fields. Above the main function, define a function called printBalance. Inside the argument list, let's set an argument called account with the type set to bank account. Next, inside the function, we're going to print the balance field. The values inside this macro will be similar to the print line macro in the main function. Lastly, let's make a copy of this function. The logic is going to mainly be the same. Instead, we're going to print the verified field. Everything in the second function should be updated to log the verified field. Our functions are ready. Inside the main function, instead of directly printing these fields, we will call both functions with the myAccount variable. After making those changes, we'll encounter an error. Take a closer look at the error. The compiler is informing us of an ownership error. It states that the myAccount variable has been removed. What exactly does that mean? As we learned earlier, variables take ownership of a value. The myAccount variable has ownership of the bank account value. However, we're passing on the myAccount variable to the printBalance function. During this process, Rust gives ownership to the printBalance function. Therefore, the myAccount variable in the main function has lost ownership. By having ownership of the variable, the printBalance function will be able to access the values stored in the variable. After the function is finished running, Rust will release memory allocated for the variable. It's dropping the value, which leads us to our error. The printVerified function wants access to the variable. At this point, it's been dropped. Therefore, the printVerified function will not be able to print the variable. The error message should start to make sense. It's telling us the ownership of a variable has been moved. We can resolve our issue by using a feature called borrowing. For example, let's say your neighbor wants to borrow your lawnmower. The idea of borrowing is to give temporary possession of something you own to someone else. Assuming your neighbor is trustworthy, they will give back your lawnmower. This idea of borrowing can apply to programming. Rust allows us to borrow variables from other functions. We can modify our functions to borrow the variable rather than taking ownership. Before the type annotation in both functions, we're going to add an ampersand symbol. By adding this symbol, Rust will prevent the function from taking ownership away. Instead, it'll allow the function to borrow the value for reading purposes. After the function is finished running, Rust will not drop the value. Ownership will continue to belong to the myAccount variable. Inside the main function, we're going to add the ampersand symbol to the arguments in both functions. We're telling Rust to allow these functions to borrow the variable's value. The functions will ask to borrow the value. The ampersand symbol will need to be added to the argument list and function calls. After making those changes, the compiler will stop complaining. Let's try compiling our project. As expected, we get the same output. This behavior is very important to understand. Rust is memory efficient. By default, it can transfer ownership across functions. If that's not what you want, you can override the behavior by telling the compiler to borrow the value. In this lecture, we are going to talk about one final concept before moving on to WebAssembly. I know you're excited to get started. I promise this is the last topic before working on a real project. There's a special type in Rust called result. It's a very common type. You'll likely encounter this type whenever working on a project. The idea of the result type is simple. The result type can store two types of values, a valid value or an error. Just because our code compiles doesn't mean we won't encounter errors. For example, let's say we need to open a file. What if the file fails to open? Here's another scenario. We may need to connect to a database. It's possible the hosting provider may be down. External forces beyond our control can cause errors. Rust provides a type for storing errors or values. Let's give it a try. Above the main function, let's define a function called isVerified. This function will accept an argument called account annotated with the bank account type. For extra precaution, we should borrow the value by adding the ampersand symbol at the beginning of the type. As the name suggests, this function will check if an account is verified. If they are, we will return a Boolean value. On top of returning a Boolean value, we should throw an error if the account is not verified. There are two possible scenarios. Either the account can be successfully verified, or it produces an error. For the return type of this function, we will set it to result. We can hover our mouse over this type to learn more information. An error will appear, but we can ignore it. Scrolling to the bottom, we're given a description that says the following. Result is a type that represents either a success or failure. The result type can act as a container for more data about the results. The compiler requires us to annotate the values for successful or failed operations. We can do so with a feature called generics. You can think of generics as function arguments, but with types instead of values. They're commonly used with functions and structures. Generics can be added to a type by adding a pair of angle brackets. Inside these brackets, we can specify the values contained in the result type. The first type will correspond to a successful result. The second type will correspond with the error. For this demonstration, we're going to set both types to Boolean types. We can begin writing the logic for the function. Inside the function, we're going to run a match on the account.verified property. Let's handle both scenarios. The field can either be true or false. If the field matches with true, we are going to return a function called OK. We are obligated to return a value with the type of results. The OK function will return this type for us. Inside this function, we can add the value for a successful result. It must correspond to the first type in the generic. Earlier, we specified the result type would contain a Boolean if the operation was a success. Let's pass in true. What about errors? Turns out there's a function for producing a value with the result type for errors. Let's return a function called error. Same as before, in our generic, we specified the type for the error value will be a Boolean. Let's pass in false. We can begin handling the result. Switching back to the main function, we're going to store the result in a variable. The name of the variable will be called verification status. The value will be the isVerified function with the myAccount variable. Remember to add the ampersand symbol. The function is expecting to borrow an account. Lastly, let's print the variable with the printLine macro. The results can't be printed directly. They must be formatted beforehand. We're finished. Let's try compiling the project. In the output, we'll find the return value contained in the result type. However, it's not entirely ideal. In most cases, we're not interested in the result container. You may want to directly grab the value. Here's where things get interesting. Rust offers various solutions for accessing a value from a successful result. We're not going to be able to explore every option, but let's look at the most common approaches for retrieving a value. The first option is to chain a function called unwrap on the results. The unwrap function is a function you will come across often. It'll grab the value from a successful result. Let's try compiling the project again. This time, the value is retrieved. What do you think would happen if the result contained an error? Let's find out. Inside the myAccount variable, I'm going to update the verified field to false. Next, I'll compile the project. By default, Rust will panic when an error is thrown by our function. The unwrap function will never return a value. As a result, we can never view the results. The error produced by Rust should give you enough information as to what's going on. There's an alternative function called the expect function. Let's replace the unwrap function with the expect function. The expect function performs a similar task to the unwrap function. It'll retrieve the value from a successful result. However, it'll allow us to output a custom error message if an error is given. We can write the message inside the expect function. Let's pass in the following message: unable to unwrap results. Time to compile the project one more time. Rust will output the same error message with our error message mixed in. Perfect! We have two functions for grabbing the response from a result type. Admittedly, this isn't the best example of how to use the result type. We have complete control over when an error gets produced. The purpose of the result type is to handle actions that can produce an error. When we start working on the mini project, we'll come across real examples of how we can use the result type. There's one more thing I want to mention. In the resource section of this lecture, I provide a link to a chapter from the official Rust book. Error handling is a big subject in the Rust community. There are various opinions and approaches to handling errors. It's not as simple as it may seem. A good starting point for learning more is this chapter from this book. I highly recommend giving it a read after finishing this mini course. In the next lecture, we are going to begin developing a real WebAssembly project. I hope you're ready. It's going to be a great learning experience. I'll see you there. In this lecture, we are going to start working on the mini project I have planned for this course. Before digging into the code, let's find out what we'll build. We are going to develop an image processing app. For the sake of simplicity, the app will apply a grayscale effect to an image. Users will be able to upload their colored images to convert to a black and white image. It's a simple project, but it'll give us insight into building WebAssembly projects. By the end of this project, you will know how to expand it to include other effects. For example, it should be pretty easy to resize images, add a blur effect, or crop an area of an image. In fact, I encourage you to explore other effects after finishing this course. Let's get started. The first step is to generate a new project. Unlike before, we're not going to generate a binary project. Generally speaking, projects can fall into one of two categories. We have binary and library projects. Up until now, we've been creating binary projects. A binary project compiles to an executable program. Users can run this program on their machines. By default, Cargo generates binary projects. On the other end of the spectrum, there are library projects. These projects compile into dependencies for other projects. If you think about it, that's what we need for our current project. We're not going to ask users to run an executable file on their machines. For safety reasons, browsers don't allow users to run executables in the browser. We are going to be using HTML and JavaScript for handling the UI in the browser. Rust will handle processing files. We can think of Rust as a dependency for our project. Therefore, it makes sense to create a library project instead of a binary project. Creating a library project can be done through the cargo init command. Inside the command line, add the following command: cargo init lib. The library option will generate a library project. We can run the command to initialize the project. After a couple of moments, a new project should have been created. It's not going to be much different than a library project. Let's quickly explore the files. The first file is the cargo.toml file. Nothing will change in this file. Cargo produces two tables, which are called package and dependencies. We're already familiar with these tables. We won't review them again. Back in the file tree, there's a folder called source with a file called library.rs. Unlike before, Rust does not define a main function. Library projects do not need to define this function. Previously, if this function was not defined, the compiler would throw an error. It's not necessary for a library project. By default, Cargo has generated a test for our library. Testing Rust objects is a topic we won't be covering in this course. It's safe to empty out the file. In the next lecture, we are going to begin adding Webpack to process Rust files. In this lecture, we are going to install Webpack for creating a development server, compiling Rust, and bundling our files. You may be familiar with Webpack. It's commonly used by frameworks like React, Angular, or Vue. If not, let's quickly talk about Webpack. In the resource section of this lecture, I provide a link to the official site for Webpack. Webpack is a tool for optimizing JavaScript projects. Developing an application takes hundreds of files. Splitting your project into separate files is great for development. For production, it's not ideal. Downloading a web app should be as fast as possible. To guarantee the fastest download time, the size of our app should be small. Webpack can help us by minifying, concatenating, and optimizing our project. Projects can go from hundreds of files to about a dozen files. But wait, there's more. Webpack can compile other languages, like Rust. We're going to be using Webpack to help us automate the process of compiling our code. It's going to take a lot of work to get the desired behavior, but it's going to be worth it. Anytime we make changes to our project, Webpack will automatically compile our code. Let's get started. Open your project in your editor. The first step is to initialize npm. This course assumes you have some knowledge of JavaScript. Therefore, I expect you to know what npm is. We aren't going to cover the basics of Node or npm in this course. Inside the command line, we can initialize npm with the following command: npm init -y. This command will create a package file. We're going to need to keep track of our dependencies. Next, we can begin installing Webpack. Inside the command line, run the following command: npm install -d webpack webpack cli webpack dev server. We are installing 3 packages for Webpack. While the installation is running, let's talk about these 3 packages. Webpack is a modular library. It's packed with features for handling various types of projects. While that's great and all, we may not need every single feature. We are encouraged to download what we need. The first package is called Webpack. It's the core functionality of Webpack. In almost all cases, you will need to download this package for bundling files. Up next, we have the Webpack CLI package. This package is a tool with dozens of commands for controlling Webpack through the command line. It also has other tools for working with plugins, which can be helpful if you want to develop a plugin for Webpack. Lastly, we have the development server. WebAssembly does not work with the file protocol. Files must be delivered via a server. Paying for a server is not ideal for development. Luckily, this package will prepare a server on our local machines. We don't need to write server-side code to start a development server. These dependencies will be enough for working with Webpack. Once you're finished downloading those dependencies, let's start configuring Webpack in the next lecture. In this lecture, we are going to configure Webpack. This process is going to involve a couple of steps. First, let's take a moment to understand what we're trying to accomplish. We need Webpack to process HTML, JavaScript, and Rust. Compiling Rust with Webpack will be another lecture. We're going to focus solely on HTML and JavaScript. The stages of bundling code look like this. First, we have our project code. Our code is given to Webpack for processing. After a few moments, Webpack will spit out a bundle. Webpack needs some information about our project before it can begin the process of bundling our code. First, it needs the entry point. The entry point can be considered the root JavaScript file. The root file is responsible for importing files. Second, it needs the output for the bundle. We can tell Webpack where to upload our project's bundle. If we configure these settings, Webpack will take care of the rest. To get started, we need to create a configuration file. By default, Webpack will search for a file called webpack.config.js in the root directory of our project. Let's take a moment to create this file. Inside this file, we're going to export an object through the module.export property. The object we're exporting will contain the configuration settings for Webpack. As mentioned before, we should tell Webpack where to find our files. In the resource section of this lecture, I provide a zip file with some starter files. Before continuing, download it. In a moment, we're going to need it. Typically, JavaScript applications are written in a directory called source. However, Rust has claimed this directory. We should keep our Rust and JavaScript codebases separate. Luckily, we're not going to heavily write JavaScript. Inside our project, create a folder called public. The public folder will house our HTML and JavaScript files. Let's drag and drop the files from the zip file to this directory. I'm going to quickly do that. I'm providing a total of 2 files. Let's explore them. The first file is the index.html file. There's not much to say about this file. There's a lot of code, but you can mostly ignore it. At the top, I'm importing Tailwind and a font from Google. Both files are served from external sources. They're going to make our app look cool. The most important tags in this file can be found near the bottom of the document. I've added HTML comments above the elements. They're the input and image tags. In a future lecture, we are going to listen to an event on the input element for file uploads. The image tag will be updated when the file has been processed. I've taken the time to assign IDs to both elements. We will select them from the JavaScript file. Speaking of JavaScript, let's open the main.js file in the public folder. There isn't a lot happening in this file. We're keeping it simple by logging a message. As you can see, we're developing a small app. Let's begin loading these files. Switch back to the Webpack configuration file. Inside the object, we're going to add a property called entry. The entry option allows us to specify a path to a file. In our case, we want to point to the JS file. Set this option to the following: public/JS. We're using a relative path. Make sure to add the ./ characters. Next, we can begin specifying the output. The output is where we can tell Webpack where to store the bundle. Add a new property called output with an initial value of an object. The configuration for the output is going to be more complex than configuring the entry. Webpack would like two pieces of information, which are the name of the directory and file. We can set the directory by adding the path property. The value for this property must be a full system path. We can't use a relative path. Node.js has a package for generating full system paths. At the top of the file, import the path package with the require function. Next, we're going to set the path property to the path.resolve function. This function accepts a list of paths to append together. We're going to pass in a constant called __ directory name and a directory called distribution. The directory name constant is defined by Node. This constant returns the path of the folder to where the current JavaScript file resides. Afterward, we're telling Webpack to place our files in a directory called distribution. It's common practice to use this name. You're more than free to change the directory name. Afterward, let's add an option called file name. This option is for configuring the name of the file produced by Webpack. Feel free to use whatever name you would like. I'm going to call our file index.js. We're almost finished. We've bundled the JavaScript file, but not the HTML file. By default, Webpack does not provide full support for HTML files. Luckily, there's a plugin for helping Webpack create HTML files. Inside the command line, run the following command: npm install -d HTML Webpack plugin. The package we've installed is a plugin for processing HTML files with Webpack. Let's give it a try. Back in the configuration file, import the HTML Webpack plugin with the require function. A plugin extends the behavior of Webpack. There are various plugins available. Configuring them with Webpack tends to be a similar process. Inside the configuration object, we can add an array called plugins. Next, we can create a new instance of the HTML Webpack plugin object. The new instance will configure the plugin with Webpack. It's very hands-off. However, we should tell the plugin where it can find the HTML file. By default, this plugin will generate a custom HTML file. We can override this behavior by passing in an object with a property called template. The value for this property must be a relative path to the HTML file. Pass in the following value, public/index.html. With that final piece of the puzzle in place, we're finished. Let's start the development server. Open the package.json file. We're going to outsource the commands to the scripts object. Replace the current command with a new command called serve. If this command gets executed, we'll run the following command, webpack serve mode equals development. The webpack command is available through the webpack CLI package. The serve subcommand will tell webpack to create a development server. With this single command, we can avoid writing a custom server. Lastly, we're setting the mode option to development. Webpack ships various modes with different optimization settings. Webpack will optimize the bundle for development, which can be helpful for debugging. Next, let's add another command called build. The value for this command will be the following, webpack mode equals production. We're using the webpack command again. This time, we're setting the mode to production. The bundle will be optimized for deploying to production servers. Our commands are ready. Let's give our development server a test. Inside the command line, run the following command, npm run serve. After a couple of seconds, Webpack will generate a bundle. During development mode, Webpack will watch our files for changes. If we modify our files, the bundle will get refreshed. This is the power of Webpack. Inside the command line, a preview URL will be provided. Let's open this URL in our browser. Here's our app in all its glory. Finally, we're ready to start processing images. The first step is to start reading files uploaded by the user. We'll begin this task in the following lecture. In this lecture, we are going to read the files uploaded by the user. Accomplishing this behavior is going to require careful thought. The ultimate goal is to send the file to our Rust program. From there, the Rust program will be responsible for processing the image. After the image has been processed, the image will be given back to JavaScript. Lastly, the image will be presented to the user. The question becomes, how do we send an image back and forth between languages? That's what we're going to learn in this course. First things first, we should start intercepting the file upload with events. For this entire lecture, we're going to be working inside the main.js file. Define a function called init. We're going to contain everything from this function. Next, let's call it. The first step is to select the input element in the document. As I mentioned in a previous lecture, I've given IDs to the most important elements. This includes the input element. Create a variable called input. Its value will be the document.getElementById function. The ID of the element is called upload. Next, we can listen to events on this element by calling the addEventListener function. The name of the event we'll listen to is called change. The change event is fired whenever the user has uploaded a file on the input element. Next, pass in an arrow function. We can begin reading the file. We're going to be using a class called FileReader. If you've never heard of this class, that's fine. It's an official class defined by the browser. It allows us to store files in JavaScript. Before we can send a file to our Rust app, we need to store the file in our JavaScript app. At the top of the function, define a variable called FileReader. Its value will be a new instance of the FileReader class. The next step is to start reading the file data. At the moment, we're listening to an event to accept the file, but we aren't storing it locally. We have the option of storing it immediately, but there's a reason we're going to avoid doing so. In the resource section of this lecture, I provide a link to a list of methods defined by this class. Browsers give us various options for reading a file. The method we're interested in is called read data as URL. At this point, I should clarify why we're going to be using this function over storing the raw file. Technically speaking, we don't need the file reader class. Files are accessible through the input element. In this code snippet, we have access to the list of files through the files property. Input elements can store multiple files, but for this example, we're going to focus on a single file. The list of files are zero indexed based. The first file can be retrieved with an index of 0. The value stored in this list is called a file object. A file object represents the file uploaded by the user. So, you may be thinking, why are we going through the trouble of using the file reader class? Image files are stored with binary data. This type of data can't be read by humans but by machines. It's not a huge issue, but it does present some problems. Transferring files between programs can be a tough task. But do you know what's not hard to do? Sending strings. Sending a string between JavaScript and Rust is easy. The same is true vice versa. Rather than transferring binary data, we should transfer string data. The file reader class can help us with this type of action. It can convert a binary file into a string with base64 encoding. Base64 encoding was introduced to address the problem we're facing. We can skip the hassle of transferring raw files. Transferring text or strings is way easier. The idea of converting an image into text sounds bizarre, right? Luckily, we don't need to concern ourselves with the details of how it works. As long as we can transfer files between languages, we're good to go. Inside the function for the event, call the fileReader.readAsData URL function. This function has one argument, which is the raw file. We'll pass in the following: input.files0. The readAsData URL function will convert our file into text. Let's grab the file. Browsers will store the text representation of a file on the result property. However, we're not going to access it immediately. The larger the file, the longer it may take to process. We should wait for the file to be read. Below the file reader variable, we're going to update the onLoadEnd property to an arrow function. This function will get called whenever the file is loaded. At this point, it's safe to access the file. Inside the function, create a variable called base64. Its value will be the fileReader.result property. Next, let's log this variable. I think it'll make things easier to understand by logging the value. We should also log the raw file object. Above the log the input.files0 element. We'll be able to compare the values. Switch over to the browser with the developer tools opened. I'm going to quickly upload a file. After uploading a file, the information was logged in the console. The first log will be the file object. It acts as a wrapper around the binary file data. After this object, a massive wall of text was logged. Believe it or not, these values represent the same file. Take my word for it. Transferring text is easier than transferring file objects. Before we move on, there's one modification I would like to make. Looking closely at the beginning of the string, browsers will add metadata to the encoded value. This portion of the text is not part of the base64 encoding format. It's additional information for the browser. Rust is not going to need this information. Let's remove it. Switch back to the JavaScript file. We're going to chain a function called replace on the result property. At the end of the day, we're dealing with a string. We have access to every JavaScript string method. The replace function will perform a regular expression on a string. I'm going to paste in a regular expression. Pause the video to copy what I have. The regular expression I pasted in will search for the metadata prefixed to the string. If it finds a match, let's replace it with an empty string. Time to give our app one more test. Try uploading a file. We've successfully removed the metadata. We can proceed to transfer the file from our JavaScript application to our Rust application. Let's begin this process in the next lecture. In this lecture, we are going to configure Webpack to compile Rust. Our file is ready to be sent over to Rust. There's just one problem. Rust does not run in the browser. We can't compile Rust to an executable file. Rust needs to be compiled into a WebAssembly file. We can perform this process manually, but I would rather automate this process. Webpack is capable of refreshing the application whenever we perform changes in our JavaScript files. It would be convenient if it can compile our Rust program into WebAssembly too. In the resource section of this lecture, I provide a link to a plugin called WebAssembly Pack. This project was developed to compile Rust projects into WebAssembly. It works out of the box. Best of all, it ships a plugin for Webpack. We can integrate this tool into our build flow to compile Rust into WebAssembly. If you click on the install link, you will be provided with various installation methods. This tool can be installed with npm. Let's give that a try. Switch over to your terminal. Inside the command line, run the following command: npm install -d at wasm tool/wasm pack plugin. Next, we can start configuring this plugin with Webpack. Open the webpack.config.js file. At the top of the file, import the wasm pack plugin with the required function. Lastly, let's register the plugin with Webpack. Inside the plugins array, add a new instance of the wasm pack plugin object. Our plugin is going to need more information about our project. Specifically, it needs to know where to find our Rust project. It just so happens that our Rust and JavaScript apps are written in the same directory. We can configure the location of our project by passing in an object. In this object, add a property called createDirectory. The value for this property must be a full system path. We have an idea of how to generate a full system path with the path.resolve function. We'll pass in the __ directory name constant with a dot. Overall, this function should return the root directory of our project. This plugin will search for the cargo.toml file. Make sure you're pointing the plugin to the root directory of the Rust project. Some beginners will try to point it directly to the source directory. There's one more modification we need to make. Open the cargo.toml file. We are compiling Rust to WebAssembly. By doing so, you can define functions that are accessible via JavaScript. By default, Rust assumes we're going to be calling Rust functions with Rust code. We should tell Rust that we'll be able to call our functions from other languages. We can do so by adding a table called library. Under this table, set the crate type option to cdylib. The word crate is synonymous with the words library or package in other languages. During compilation, Rust produces a crate. We're telling Rust to produce a crate with support for external languages. We're finished configuring Rust. It's time to give our compiler a test. Inside the command line, run the npm run serve command. After a couple of sections, Webpack will compile our project. It's also going to make changes to our project. We have a new directory called package, which is abbreviated to pkg. This folder will contain a copy of our WebAssembly files. It's possible you may not see a WebAssembly file. That's perfectly fine. We haven't written code for WebAssembly. As long as your project is being compiled, you should be good to go. If you receive warnings from Webpack, that's fine too. They will go away as we work on our project. In the next lecture, we're going to start writing some WebAssembly code. In this lecture, we're going to import the WebAssembly file generated by Webpack. There are a couple of adjustments we're going to perform in our configuration files. In the resource section of this lecture, I provide a link to a crate called WASM bind gen. This crate will help us export Rust functions into JavaScript. We could write the code ourselves, but why reinvent the wheel? This crate is the most popular package for helping us expose functions to JavaScript. The same is true vice versa. We can expose JavaScript functions into Rust. You can think of it as the glue between Rust and JavaScript. You may be thinking, what about the crate type option? In the previous lecture, we added the crate type setting to our configuration. This setting allows us to communicate with any language other than Rust. However, Rust doesn't know which language we are trying to communicate with. This crate will close that gap. It allows direct communication between Rust and JavaScript. We can download this crate by including it in our configuration file. On the right side of the page, there's a section called Install. There's a code snippet we can click on to copy to our clipboard. After copying this line, open the cargo configuration file. We're going to paste this code below the dependencies table. Dependencies must be listed under the dependencies table. The format for a dependency is the name followed by the version number. As of the recording of this course, the latest version is 0.2. If you're using a newer version, that's perfectly fine. Before compilation, Cargo will scan our configuration file for dependencies. If it finds a dependency, it'll automatically download the dependency before compiling our project. We don't need to perform this step in the process manually. Let's move on to importing WebAssembly. Open the main.js file in your editor. Importing a WebAssembly file is the same as importing a JavaScript file. We can use the import function to import a file. Importing a file is an asynchronous operation. Therefore, we should add the async keyword to the initialize function. Next, we're going to import the WebAssembly file. At the top of the function, define a variable called rustapp with an initial value of null. Next, we're going to write a try-catch block. Importing a file can potentially fail. We should stop the function from running before executing further code. We are deciding to import Rust before listening to events in our script. It doesn't make sense to listen to events when Rust can't do anything with the data. Inside the try block, update the Rust app variable to the import function with the await keyword. The path to the file is the package directory. The package directory is created by the WebAssembly Tools plugin. One of the benefits of using this plugin is exporting WebAssembly files. Inside this directory, there's a file called index.js, which is responsible for exporting WebAssembly. It's an abstraction layer for importing WebAssembly. As long as we import this file, our Rust program will be imported into our function. If this import fails, we should handle the error. Inside the catch block, log the error with the console.error function. Subsequently, return the function. Lastly, let's say the import is a success. After the try-catch block, log the Rust app variable. There's one final line of code we need to add to our project. WebAssembly is an experimental feature in Webpack. Keep in mind, it's a relatively new feature with slow adoption. We're not entirely sure of the implications of WebAssembly yet. We need to tell Webpack to enable support for WebAssembly. Open the Webpack configuration file. At the bottom of the object, add an object called experiments. We can turn on experimental features from this object. The feature we're interested in enabling is called async WebAssembly. We can turn on a feature by setting the value to true. After making those changes, we should be able to run our project. In the command line, run the npm run serve command. Compiling the project may take some time. We added a new dependency to our Rust project. Cargo needs to download this dependency, compile it, and build it. This process may take a while. Be patient. After the project has been compiled, let's check it out in the browser with the console opened. Perfect. The file has been successfully imported. We can start calling functions from Rust in our JavaScript code. Let's begin setting up a function in the next lecture. In this lecture, we are going to begin defining a function in Rust. The job of this function will be to transform an image into a grayscale image. Before we get into the heavy stuff, we should try to log the file from Rust. At the moment, we're logging the file from JavaScript. If the file can be logged from Rust, we can confirm a relationship between JavaScript and Rust. To begin, let's open the main.js file. Search for the onloadEnd function on the file reader object. Inside this function, we are logging the base64 variable. Let's replace the console.log function with a function called rustapp.grayscale. The argument can stay in place. The rustapp variable is a module. Like all modules, we can access methods and properties exported by the module. You may get an error if you're running Webpack in the background. It's because we haven't defined this function. Let's take care of that. Open the library.rs file. Inside this file, define a function called grayscale. As we learned previously, we are expecting a string from JavaScript. In the argument list, add an argument called encoded file. The type will be set to string, which will be borrowed. We are borrowing the string because we're not going to update the string directly. The purpose of encoding the file was to transfer it between JavaScript and Rust. Mission accomplished. Once we've received the file, we're going to transform it back into binary data. Once we have the binary data, we can begin to manipulate the image. It is possible to manipulate an image through a string. Unfortunately, it's not ideal or common. We're not going to go through the trouble of manipulating images with strings. It's much easier to work with binary data. Luckily, base64 is a highly popular encoding format. Rust has support for decoding base64 strings. Before we get there, let's log the string to confirm it's been transferred. First, we need to expose this function to JavaScript. By default, functions are not accessible to external files. However, we can make a function public by adding the public keyword to the function. The public keyword will make a function public to Rust. However, it doesn't make it public to JavaScript. Luckily, the WebAssembly bindgen crate can export functions to JavaScript. Above the function, we're going to add a hash character followed by a pair of square brackets. I'm introducing a new feature called macro attributes. Attributes are a feature for running macros on a function. So far, we've used macros to create values. But what if we want to apply a macro to a function definition? We can use attributes to run macros on functions. The name of the macro can be written inside the square brackets. For this example, we're going to run the WebAssembly bindgen prelude WebAssembly bindgen macro. What a mouthful. The bindgen crate exports a macro for handling the action of exporting a function to JavaScript. The actual macro is the bindgen portion of this code. We may need to export multiple functions. I think it would be annoying to constantly type this line. We can shorten this line by using the use keyword. At the top of the file, add the use keyword. The use keyword allows us to access a specific function or macro from within a crate. We'll be able to reference the macro by its name instead of typing the full path. Let's copy and paste the path. Next, we can shorten the macro to just bind gen. This results in the same thing. It's an optional step but can make your code readable. In some examples, you may see developers replace the bind gen macro with a star character in the use statement. The difference is that the star character will shorten all functions and macros defined under the prelude path. Either solution works. Feel free to use whichever solution you prefer. The next step is to begin logging the encoded file. We have two options at our disposal. We can write the code for logging a value, or we can use a crate. I think using a crate will be easier. You'll likely come across the crate I'm about to mention. In the resource section of this lecture, I provide a link to a crate called Web System. The Web System crate exports a set of JavaScript functions to Rust. This crate is completely different from the bind gen crate. The bind gen crate exports functions, but it does not define the functions themselves. We are responsible for writing the logic, whereas the Web System crate exports JavaScript functions defined by the browser. This includes the console.log function. Let's open the cargo configuration file. Next, add a table called dependencies.websystem. Normally, dependencies can be listed under the Dependencies table. However, Cargo is a very efficient package manager. We have the option of partially importing the features we need from a crate. We don't need to download the entire package. The bind gen crate is lightweight, but the Web System crate is not. We can specify a list of features by creating a separate table with the name of the crate appended at the end of the table name. Below this table, we can set the version by adding the version option. The latest version is 0.3.4. Next, we can add an option called Features, which will be an array of features to download. In this array, we're going to download the console feature. The console feature will export JavaScript's console functions to our Rust project. We don't need anything else, so let's go back to the Rust file. We can start calling the Web System crates functions, but we should add their paths. Below the first use statement, add another one. We're going to add the following path: Web System console log 1. The Web System crate defines several logging functions. The number refers to how many values can be logged. For example, the log1 function will log one value. The log2 function will log two values. So on and so forth. We don't need the other log functions. This function will suffice. We can make our code readable by adding an alias. Instead of referring to the function as log1, we can add the as keyword to create an alias. The name of the alias will be called log. Let's use our new function inside the grayscale function. Call this function with the encoded file variable. This function wants to borrow the string. We'll need to add the ampersand symbol. We're going to receive an error. To understand why, let's hover our mouse over this function. This function is expecting a type called JSValue. However, we're passing in a string. Rust strings are not equivalent to JavaScript strings. At the end of the day, we're calling a JavaScript function. We need to perform type conversion. After the encoded file argument, chain a function called into. This function is one of the most interesting features of Rust. Type conversion can be performed by calling the into function. The into function will intelligently detect the data type we're converting to. It understands we're trying to convert a string into a JS value. There's a lot more going on, but that's the basics of things. Let's save our file and open the browser. I have Webpack running in the background. I will always have it running for the remainder of this course. With the console opened, I'm going to upload a file. Wow, we've successfully transferred the file to Rust. It's magically logging the same value we logged in our JavaScript file. Isn't that amazing? It's time to start transforming the image. Let's begin transforming our images in the next lecture. In this lecture, we are going to decode the base64 string into binary data. In the resource section of this lecture, I provide a link to a crate called base64. It's a simple crate for encoding and decoding base64 values. We're going to use it to convert the string back into binary data. First, let's copy the installation code from the documentation page. Next, open the cargo configuration file. Below the dependencies table, paste in the installation code. Lastly, let's use it in our project. Open the library file. At the top of the file, we're going to import a function called base64decode. The decode function will convert a base64 value into a vector. Let's use it in our function. Before we do, I'm not interested in logging the file anymore. Let's replace the encoded file argument with a string that says the following: grayscale called. Next, let's begin decoding the value. We're going to store the binary data in a variable called base64toVector. The value for this variable will be the decode function with the encoded file argument passed in. If we hover our mouse over this function, we'll be given more information about the type of value returned by this function. It's going to produce a result type. A few lectures ago, we talked about this type. Decoding a file can potentially cause an error. For demonstration purposes, we're going to assume the file can be decoded. We'll chain the unwrap function to grab the result. We should check the type of value wrapped by the result type. According to the editor, the type for the successful result will be a vector with a collection of U8 values. The U8 type is a type for numbers. The letter U stands for unsigned. Unsigned numbers are always positive. Binary data is always positive. We don't need to store negative numbers. Let's log a message to let us know the value was decoded. Below the variable, call the log function with the following message: image decoded. Next, let's try uploading an image. Open the console in the browser. After doing so, upload an image. In the console, we'll find two logs. Our Rust application is telling us the grayscale function has been called, and the image has been decoded. Awesome! We can start to load the image. Let's take care of this step in the next lecture. In this lecture, we're going to load an image into a library called image. In the resource section of this lecture, I provide a link to a crate called image. This crate exports functions for manipulating images. We're going to use it to help us apply a grayscale effect to an image. Technically, we don't need this package. As long as we have the binary data, we can change an image's appearance by modifying the binary data. It's an advanced topic, which won't be covered in this course. It's going to be simpler to use a crate for interacting with an image's binary data. Let's copy the installation code. Next, open the cargo configuration file. Lastly, paste the crate below the dependencies table. Hey everyone, it's me from the future. The image crate was recently updated. Unfortunately, this update will produce errors in our project. To prevent these errors, I highly recommend using the same version in my video, which is 0.23.14. Versions 0.24 or higher will cause problems. Alright, back to the video. Time to start loading the image. Open the library file. At the top of the file, we're going to import a function called image_load from memory. The load from memory function will store a copy of the image for manipulation. The goal is to pass our binary data onto the image library for processing. Let's give it a try. Inside our function, we're going to create a variable called image. Its value will be the load from memory function. We can hover our mouse over this function to learn about the type of value accepted by the function. It wants to borrow an array or vector of binary data. Luckily, the decode function returns a vector. We can pass on the base 64 to vector variable to the function with the ampersand character. Next, we need to unwrap the value. If we look at the description again, the description states the return value has a type of image result. The image result type is a variation of the result type. We can chain the unwrap function to grab the successful result. Next, let's call the log function with the following message: image loaded. Time to give our app a test. If we did everything right, we should see the image get loaded. Try uploading a small file. I don't recommend uploading large files. The larger the file, the more processing power it'll take. The response from our application will take a while. If the response takes a while, I recommend using a smaller file. After a few seconds, the image has been loaded. We can move on to changing the colors of the image with Rust. Let's handle this action in the next lecture. In this lecture, we're going to apply a grayscale effect to our image. We loaded the image with the load from memory function from the image crate. Currently, I'm looking at the documentation for this function. I'll provide a link to this function in the resource section of this lecture. According to the documentation, the load from memory function returns an image result. We unwrapped the result to grab the image. The value we wrapped by the image result is called a dynamic image. We can click on this type to learn more. You can think of the dynamic image as an object with methods for interacting with the image. On the sidebar, you'll come across dozens of methods. The method we're interested in is called grayscale. The description says the following: return a grayscale version of this image. It's exactly what we're looking for. Looking closely at the argument list, it's going to borrow a value called self. You can think of the self keyword as the this keyword in JavaScript. It represents the value the method was called on. We don't need to pass on data to this method. Instead, it'll automatically pass on the image to this method. If we look at the return value, it'll return another dynamic image. We should store this image after calling the function. Let's get started. Open the library file in your editor. In the grayscale function, we're going to add the mute keyword to the image variable. After calling the grayscale method, we're going to override this variable with the new image. We don't need the original image after transforming it. Afterward, let's update the image variable to the following value: image.grayscale. Next, we're going to log the following image: grayscale effect applied. With a single line of code, we've applied a grayscale effect to an image. The image crate is extremely powerful. It can perform other transformations such as resizing, cropping, and blurring. For this demonstration, we're going to apply a single effect. However, you're more than free to modify this project to apply other effects. Let's try uploading an image with the console opened. Processing an image does take time. Once again, I recommend uploading a small file. Otherwise, WebAssembly may take a while to log a message to the console. After you've received the message from WebAssembly, we can begin sending the image back to the user. Let's tackle this step in the next lecture. In this lecture, we're going to create a buffer for an image. You may have heard of buffering if you watch YouTube. The idea of a buffer is a universal concept in the programming world. Before we get into the code, let's talk about buffers in general. Buffers are a feature for temporarily storing data. You can almost think of them as variables, but more powerful. You may not know it, but you're using a buffer right now to watch this video. Variables are great for storing numbers, characters, or arrays. What if we want to store file data? We can use a buffer. Have you ever watched a video on YouTube? I bet you have. Video files are extremely large. The file size of a video can be measured in gigabytes. Imagine if we lived in a world where you would have to download a video before watching it. You would be waiting an hour to watch a 10-minute cat video. Luckily, we don't live in this kind of world. We can watch videos almost immediately. On the video player, a portion of the timeline is colored in white. This indicates how much of a file has been downloaded. How is that possible? How can we watch a video that hasn't been completely downloaded? The answer is with buffers. The buffer acts as a temporary storage for data. Buffers are mainly used for storing files. One of the most interesting features of a buffer is being able to read data from it. After a buffer has stored a file, we're allowed to read data from a buffer. This means we can watch videos without completely downloading an entire video. We're going to use a buffer to store the image. At the moment, our image is a dynamic image. It needs to be converted back into binary data. This conversion can take time. We won't be able to store the data all at once. Therefore, we're going to need to create a buffer to store the image until the conversion is complete. Inside the grayscale function, create a mutable variable called buffer. Its value will be an empty vector. We can create vectors with the vector macro. Next, we are going to call the image.writeTo function. The writeTo function will initiate the process of converting an image into binary data. It needs to borrow a vector as its first argument. We're going to pass in the buffer variable. The writeTo function wants to borrow this variable. However, we can't apply the borrow operator. It's because our variable is mutable. Mutable variables have a different operator for borrowing values. We can write &mut to allow a function to borrow a value. The writeTo function has a second argument for the file type. We must specify the type of image we're creating. We have the option of converting the file type, but for this project, we're going to output a PNG image. At the top of the file, we can import a value called image format output PNG. The PNG value will help the image library write a PNG image. Back in our function, pass in the PNG value. One more step. The value returned by this function is a result. We do not need to store the result, but Rust does not like that. We need to handle the result. To satisfy the compiler, we can chain the unwrap function. After writing the image, let's log the following message to the console. New image written. Let's give our app one more test by uploading a file. Great! We've successfully written the image. In the following lecture, we will finish our app by displaying the image to the user. In this lecture, we're going to finish our app by rendering the image in the browser. Before we get into the code, I want to take this moment to review the overall process. We've been performing various actions on the image. Let's review everything we've done thus far. Everything begins with JavaScript. In our JavaScript file, we're accepting an object called file. It represents the file uploaded by the user. We decided to convert this object into a base 64 string. This is because it's easier to send file data as strings. Afterward, we send the string to Rust. In our Rust file, we decoded this string into binary data. This binary data was given to a crate called image. The image crate will create a wrapper called dynamic image. This wrapper has methods for interacting with the image. We applied a grayscale effect to the image through this wrapper. At this point, we need to reverse the chain by converting the image into binary data. Next, we need to convert the binary data into a base 64 string. The string will be given back to JavaScript. From there, JavaScript can render the image. Let's begin taking the final steps. We'll continue working on the Rust file. In an earlier lecture, we imported the base 64 crate to decode a string. It exports a function for encoding a value. Let's import it. There's a cool trick for grabbing multiple functions from a single use statement. We can replace this portion of the statement with curly brackets. Inside these brackets, we can write a list of functions to import. We're interested in two functions called encode and decode. Let's scroll to the bottom of the grayscale function. We're going to create a variable called encoded image. Its value will be the encode function with the buffer variable. This function will borrow the variable. The value returned by the function will be a base 64 string. We're going to modify the string by converting it into a data URL. If you can recall, JavaScript creates a data URL. A data URL contains metadata and a base 64 string. We removed the metadata in our JavaScript file. We should add this metadata to the string to have a full data URL. Rust has a macro called format for manipulating strings. It's very similar to the print macro, except it'll return a string instead of printing a string. Below the variable, create another variable called data URL. Its value will be the format macro. The first argument will be the following value: data, image / png, base 64, comma. Next, let's add a placeholder at the end of the string. Lastly, we will pass in the encoded image variable. The last step is to return this string. Rust will throw an error because the return type is not specified. At the top of the function, set the return type to string. There are two types of strings. If we're borrowing a string, the type must be str. If we have ownership of a string, the type must be string. It's a small difference, but something to keep in mind. Our function is complete. We can start rendering the image. Open the main.js file. Scroll to the onLoadEnd function. In this function, we're calling the grayscale function. We should store the URL returned by this function. Assign the value to a variable called image_data_URL. We're not going to convert the encoded string into a file object. Browsers support base 64 images. We can use this URL to render an image. The browser will decode the image on our behalf. In our document, we have an image tag. Let's select it with the document.getElementById function. The ID of the image is called newImage. We will modify the source attribute with the setAttribute function. The value for this attribute will be the image data URL variable. Voila! We're finished. We've successfully created our first WebAssembly app. Let's give our app one final test. In the browser, try uploading an image. After a few seconds, the image has been processed. It has been converted from a colored image to a grayscale image. Hopefully, this project gives you an idea of how WebAssembly can change the world. It's a very powerful tool for building web apps. It's a completely different but fun world. In the next lecture, we're going to show our app to the world by deploying it. I'll see you there. In this lecture, we're going to deploy our app. You may have noticed how slow our app is. It's not an issue with WebAssembly. It's more of a problem with Webpack. In reality, images can be processed in under 2 seconds instead of 10. Webpack is adding additional code that slows down the processing. When we deploy the project, it's going to be faster than the development build. We have various options at our disposal. My favorite hosting service is called Vercel. It's completely free and easy to deploy a project on Vercel. We can deploy a project with a few clicks. Before deploying the project, we need to build the project. In our package file, we added a command for building the project. In the command line, run the following command: npm run build. This command will generate a new directory called distribution. These files should be deployed to production. Everything else can remain. The next step is to commit the project to GitHub. I recommend ignoring the node modules directory. In your editor, open the git ignore file. Inside this file, add the node modules directory to the list of files to ignore. We won't need to upload this directory. Next, I'm going to upload my project to GitHub. You should do the same. I'll be right back. After a few minutes, I have successfully uploaded my project to GitHub. We're uploading our project to GitHub for easier deployment. Vercel is capable of pulling a GitHub project. In the resource section of this lecture, I provide a link to Vercel. Before continuing, you will need to create an account. It's completely free. Pause the video before moving on. After creating an account, you'll be taken to your dashboard. Vercel should present you with a list of projects registered under your account. As you can see, I use Vercel for my personal projects. On this page, there's going to be a button for creating a new project. Click on it. On this page, you're going to be asked to connect your GitHub accounts. I'm going to connect mine quickly. After connecting your accounts, GitHub will present you with a list of repositories listed in your GitHub account. Import the image app we've been developing. Vercel will ask us more questions about our project. First, it'll ask if we want to create a team. We're working individually. You can skip this step. Next, we're going to point Vercel to the distribution directory. After making those changes, click Deploy. It's going to take a while for Vercel to deploy our project. Be patient. After a few minutes, we're greeted with a success message. Awesome! We'll be given a URL to preview our app. Let's check it out. It took 2 hours, but we've created a WebAssembly project for applying effects to images. Feel free to add this project to your portfolio. I'm sure it'll impress some people. If you want to take things a step further, I encourage you to do so. You can add additional effects like a blur effect. If you're taking my Angular course, I've got some exciting news. We're going to use WebAssembly to process video files. If you're not taking my Angular course, consider checking it out. Angular is a great framework to learn. Otherwise, I hope to see you again in another course. Thanks for watching.